All right, so if you take a look at number 3, we have not done one quite like this yet. The first thing that's very different about this is that this fraction is top-heavy by 1. All right, so that means what kind of asymptote are we going to have here? Oblique. And remember, you can call it oblique, or you can call it slanted. But down here in this little area, I have blanks for both horizontal and oblique. And that's a little deceptive because it's not going to be both of them. It's going to be one or the other. So it's horizontal or oblique. And since we said it's not horizontal, we'll eventually have to find the equation of your oblique asymptote is going to look like an equation of a line because it is. All right, so an oblique asymptote means that your graph is going to have some like kind of slanted tendencies far to the left and far to the right. So all oblique asymptotes will be written in y equals mx plus b. All right, but I need to show you how to actually get that today. Because I do think it's pretty easy to check out from the graph. So I'm just going to go ahead and graph it first. So in y equals, whoopsies. In y equals, you want to type in the equation. Make sure you put a decimal point after either the one up top or the one on the bottom. When you graph it, it should look like this. And kind of what you should see is, does it look like there's a vertical asymptote? And if you're not sure, remember, zooming out is always a good thing. So mine's taking forever to graph. So when I zoom out, okay, see how like right here in the middle, and actually let me turn off. Watch this for a second. I think I could, can I turn these off? Yes, okay. So I hid my axes because I think it was kind of hard to see. Okay, so this is the graph without the x and y axis shown. Now, if you look in the middle here, see how your graph looks vertical. Like, ignoring the middle parts, but if I just kind of like look at what's happening here and here, see how it's almost straight up and down? That is an indication of you definitely have a vertical asymptote. Then if I cover up what's happening in the middle, just look at the ends, what kind of line do you see there? Slanted. So the vertical asymptotes is what's happening if you kind of just look at the middle. And the slant asymptote is what's happening as you look far to the ends. Okay, so this one's going to have a vertical asymptote. So it's going to have one of these. I don't know if we have a removable discontinuity yet, but if I go into the table, if you scroll around a little bit, how many errors do you see? 1. And it's at 1. Look at your equation. Does that make sense? Okay, so remember your domain comes from your denominator. The one number that would cause that denominator to be undefined would be 1. And if we look in our table, x can't equal 1. So the domain, vertical asymptotes, and removable discontinuity, those three are connected. Okay, they all work together. Remember, whatever you exclude from your domain is either going to be one of these, or it's going to be this. Now, just based on the picture that we saw, it looks like we have a vertical asymptote. All right, but the way that we ensure that this is definitely not a removable discontinuity is the only way this is going to turn into a hole in your graph is if it cancels out. The only way it's going to cancel out is if we can factor the top and then cancel it. We try to split the middle here. 2 times -1 is -2. And the only way we can multiply to get 2 is 1 and 2. Is there any way that 1 and 2, no matter which way you put negative signs on or whatever, are ever going to give you this? No. So the top is not factorable, which means that x minus 1 is not going to cancel out. So, since nothing cancels, there's no removable discontinuities, and that just confirms for us that our vertical asymptote is the line x equals 1, which our graph was kind of telling us anyways. So I'm going to go ahead and graph that over here. So I'm going to go to 1 and draw a vertical line. All right, and then just like, yep.
Okay, so how did you get the vertical asymptote again?
It's whatever your domain restriction is.
Okay.
All right, and if it doesn't cancel out, then it becomes one of those.
Okay.
So yeah, vertical asymptotes are always going to come from what's left over on the bottom. So before you plot any like actual points on this graph, you need to get all of your asymptotes in place first, because those are kind of like your guidelines for how the rest of the graph's going to go. So the next step is we have to figure out what that oblique asymptote is. So we have to figure out an equation for it. And the way that we do it is using something that you haven't used since Algebra 2, synthetic division. Synthetic division is would you rather do long division? No. If you're saying yes, I don't know that you did long division with these kind of problems last year, because synthetic division is way easier. Okay, so let me give you a crash course on synthetic division. All right, so you're going to have numbers that go across the top, and you're going to have a little number that goes in the box over here. Now, depending on who you had for Algebra 2, they may have drawn the synthetic division set up differently. So the way that I do it is I put a box. It's really half of a box, so I don't know. It's a backwards L. And then I put the numbers that I use for synthetic division across the top next to it. The numbers that you're going to use for the top are going to be 2, -2, and -1. So whatever the coefficients of your numerator are, as long as that numerator is in standard form, which means it can't be in factored form. If it were in factored form, you have to sit there and FOIL it out. But this isn't in factored form, so we just go ahead and use the 2, the -2, and the -1. There's going to be numbers that go underneath of this, so leave yourself some space for another row of numbers. And then I'm going to draw a line. And then I always draw a line for the remainder column as well. So that last number is going to be your remainder column. So I'm going to draw that. Now, you may have had, like, I want to say, like, I think Mrs. Danhoff does it a little bit differently, where, like, some teachers draw it like this. And they'll put, like, 2, -2, -1. Okay. So, yeah, it's up to you. Like, so you may have had a teacher that did it like this. I don't care however you do it. I like my way, so that's the way I'm going to do it. But if you did it the other way and you want to do it the other way, go for it. Now, the only thing you would have used this for in Algebra 2 would have been for finding the roots of a polynomial, so like where it crosses the x-axis or that kind of stuff. And like when you did this, you would have graphed your picture, found where it crosses the x-axis, and that would have been the number that you used in this box here. Okay, so that's how you would have done it in Algebra 2. We're using this for a different purpose, so we're not going to use the x-intercept here. The thing that does go here is your vertical asymptote. So in this case, our vertical asymptote's at 1. So 1's going to be the number that we use for synthetic division to divide this out. Okay. So here's how it works. The first thing you're always going to do is drop down that initial number, no matter what it is. So in this case, that 2 gets dropped down, and it goes below the line. Your next step is to take whatever number's in the box, multiply it by the number that's down here below the line. So 1 times 2 is 2, and that number goes here. And then you're always adding those numbers down. So -2 plus 2 is 0, and then you repeat that process. 1 times 0 is 0, and then you add it down. Do you remember in Algebra 2 what this number here should always have been? 0. And it's not 0, which is kind of weird. But again, we were using it for a different purpose, to find the roots or the zeros of an equation. For our purposes, that remainder column is actually of no use to us. So you're just gonna ignore it. And a lot of times, like if you look at my keys and stuff, I don't even do this column because it does not matter what number you get there. More often than not, you're gonna get a remainder, but again, it doesn't even matter. So just leave it. And what you have left okay, if you see how I wrote that, y equals mx plus b. That first number is your slope, so that 2 would replace the x, and that second number is your y-intercept. So I can put y equals 2x plus 0, or just y equals 2x. So this is how you find the equation of an oblique asymptote. Before you draw that on paper, you want to go back to your calculator and type in that equation and make sure that it fits with the rest of your graph. So if I go back here and add another column down, not another column, but another equation, and mine's still zoomed out, and I still have the axes turned off, but you'll still be able to see it. So that went really fast, but I'm going to resume 6 it. Okay. So there it goes slowly. So there's my original graph. And you'll see the red line kind of fit in between those two pieces like a puzzle. Like it's like it was made to go there. So you have some like gap in the middle, all right, but that's normal. But if I zoom out, it almost looks like that red line and that blue graph, once you get farther away from the center, it looks like they're exactly the same line. And they're pretty darn close. Like that graph's going to ride along that slanted line forever. So like I said, if you look down here, it looks completely red. And up here, it looks completely red. But in the middle, it's kind of off a little bit. That tells you that that's the correct equation. All right, so when you go to graph this, over here, on paper, y equals 2x. So your y-intercept is 0, and your slope is 2. Up 2 over 1, up 2 over 1. When's the last time you graphed a line like this? Probably been a while. And then I'm going to connect them. All right, so you want to have all of your asymptotes in place before you draw in your graph. And then to get points to put the rest of the graph on, I'm just going to go into the table and pick out ones that are nice or nice enough. For these graphs, I try to get something that's going to plot back here, like on the left side. So I would try to get a point that's going to fit down here somewhere. So, I don't know, -4, -7.8, it's not terrible. So -4, it's almost to -8. -1, -1.5, that's not bad. But see how close it is to that line? And if you're not precise when you graph this, like if you don't use a ruler and if you don't put those points all the way across, it's going to be kind of messy because these points are going to be real close together. 0, 1. What is that point? Which one of these is that? The x-intercept or the y-intercept? The y. Some of you on your quiz, wrote this but wrote it as 1, 0. Like, be careful about how you write those. The y-intercept should always be 0 and then your number, and the x-intercept is going to be reverse of that. Let's see here. Oh, 2, 3. That's a nice one. 3, 5.5. Again, super, super close to that point. And that'll be it for when I graph. All right, but when I go back to this picture, you'll see that this graph just kind of rides along this vertical asymptotes, turns, and just kind of rides along the oblique. It's kind of, but there's the blue one is my actual graph. So I put a couple guideline points on the blue graph, but generally speaking, I just kind of use the oblique asymptote, travel it along there. Once it gets close to the vertical, just make it turn and go down, and same thing on the other side. The only thing we have left to do is end behavior and x-intercepts. Let's do end behavior first. As your graph goes to the left, so as x goes to negative infinity, where is the left part of your graph going? Negative infinity. So here, I'm going to say as x approaches negative infinity, y approaches negative infinity as well. And then as your graph goes to positive infinity, so as your graph goes to the right, where is y going? Positive infinity. All right, so whenever we had a horizontal asymptote, your y value leveled out at a number like 4 or 2 or 0 or something like that. When you have slanted asymptotes, your graph's going to go off forever to the infinities, one way or the other. We'll save the x-intercept for last. Let's talk about range. When you look at this picture, does it seem like it goes down forever? Does it go up forever? Does it seem to be any breaks vertically in this graph? So like, could you go down forever and then up to positive infinity without ever picking up your pencil? Yeah. Now, if you were to try to graph this, go this way on your graph, in order to get this second piece of the graph, you have to pick your pencil up and move it over. That's why we excluded one number on the domain, that jump in the middle. But for your range, it goes up and down forever. There's no breaks vertically in the graph, so your range would be all reals. The last part of this, the x-intercepts. Every other equation that we've done until this point, we could look at the numerator and figure out the x-intercepts, because every one we've done up until this point has been able to be factored on top. Or if it weren't factored, we could find our answer in the table. We are not so lucky on this one. I'm going to have to go back and turn my axis back on so we can actually see this. Let's see if this works. Okay. Do you see where your graph crosses the x-axis? Like, does it look like it has x-intercepts? Yeah. It's got one here, and it has one here. All right, but since the top's not factorable, we're going to have to use the calculator to find this for us. So, again, another throwback to Algebra 2. Go into, second, and then the calculate menu, option 2. It's going to ask me left bound and right bounds. This is where you move your cursor just to the left of one of your zeros. So I'm going to try to find this furthest most left one first. So I move my cursor to the left of it. I'm going to hit enter. Now I'm going to arrow over to the right a few times and hit enter. That was not the enter button. Okay, and then I guess I don't even move the cursor. Let's just round to 2 decimal places. So negative 0.37. All right, and then I have to repeat that same process to find the one that's on the right. So second, calculate, 0. Now, in order to get to this piece of the graph, I'm going to hit the right arrow a few times until you start to see it pop up on the other side. Go to the left of the one over there, to the right, and guess this one's 1.37. Again, so if you can't factor it, you could use your calculator to find your x-intercepts, or you could always use your calculator to find the x-intercepts if you like. Okay, so what I want you to try now